Welcome! Today, we will explore the problem titled Reaching Points, which is an interesting challenge designed to test your problem-solving and algorithmic skills. This problem involves navigating through a grid using specific rules to determine if a target point can be reached from a given starting point. Let's dive in and break it down step by step. In this problem, we are tasked with determining whether we can transform a starting point, Sx, Sy, into a target point, Tx, Ty, on an infinite two-dimensional grid. The transformation rules allow us to move from the current point, x, y, to either x plus y, y, or 6, x plus y, in a single step. Essentially, at every move, one of the coordinates is added to the other, which results in increasing one of the values of the point. The goal is to determine if it's possible to reach the target point using these rules, starting from the given initial point. The function should return true if reaching the target is possible, and false otherwise. The inputs provided are integers representing the coordinates of the starting and target points, and the output is a Boolean value indicating whether the target can be reached. To illustrate this problem, let's look at the first example. Here, the starting point is 1, 1, and the target point is 3, 5. Following the transformation rules, we can perform the following series of moves. Starting from 1, 1, we add the x-coordinate to the y-coordinate, resulting in 2, 1. Then, we add the y-coordinate to the x-coordinate, which brings us to 2, 3. Next, adding the y-coordinate to the x-coordinate again gives us 5, 3. From here, another transformation leads to 5, 8. By reversing the last move and applying another transformation, it's possible to reach 3, 5 from 1, 1. Therefore, the answer for this example is true, as the target is reachable. Now let's consider another example where the starting point is 1, 1, and the target point is 2, 2. Using the given transformation rules, it becomes clear that this target is impossible to reach. Both moves, x plus y, y, and x plus y, always produce points where at least one coordinate is strictly larger than the other. This means that the point 2, 2, where both coordinates are equal, cannot be achieved starting from 1, 1. As a result, the output for this example is false. In contrast, if the starting point and the target point are the same, as shown in the third example where both are 1, 1, no moves are needed, and the output is true by definition. To summarize, if the starting point matches the target point, the answer is always true since no transformations are required. Additionally, if the target point has any coordinate smaller than the corresponding value in the starting point, it's impossible to reach the target because the allowed transformations only increase the values. This problem also involves handling constraints where the coordinates can go up to 10⁻⁹, which means the solution needs to be efficient and avoid simulating every possible move. Understanding these edge cases is crucial to implementing a correct and optimized solution. To solve the reaching points problem, we initially consider a brute force approach. The intuition here is fairly straightforward. Start at the initial point, Sx, Sy, and simulate every possible move by applying the two transformations, x plus y, y, or 6, x plus y, recursively. At each step, we generate new points and check if we can eventually reach the target point, Tx, Ty. If we do, we return true, otherwise, we return false. However, the computational cost of this approach is immense. Each step branches into two possibilities, leading to an exponential growth in the number of states we need to explore. For large constraints, where Tx and Ty can go up to 10 to the power of 9, this results in an infeasible time complexity of O2 max Tx Ty. Additionally, the recursion stack itself consumes exponential space, so this method is both time inefficient and memory intensive. While simple in concept, this brute force approach quickly becomes impractical for larger inputs. Now, we consider a more efficient solution, the reverse simulation approach. Instead of simulating moves forward from Sx, Sy, to Tx, Ty, we reverse the process and work backward from the target point, Tx, Ty, to the starting point, Sx, Sy. The key insight here is that the transformations are reversible. Specifically, if the current point is Tx, Ty, and Tx, Ty, the previous point must have been Tx, Ty, Ty. Similarly, if Ty Tx, the previous point would have been Tx, Ty, Tx. By working backward, we avoid generating all possible forward states and instead focus only on valid paths. It's also crucial that both tx and ti remain positive throughout the process. This backward simulation continues until either we reach sx, sy, in which case we return true, or we determine that no valid path exists. Additionally, if one dimension matches the starting point, we can directly check whether the other dimension can be reached using the modulus operation. This drastically simplifies the process and prevents unnecessary computations. The efficiency of the reverse simulation approach lies in its use of modulus operations. Each step significantly reduces one dimension, resulting in a time complexity of O log max tx ti. Unlike the brute force method, this approach avoids exponential growth and instead operates in logarithmic time. Furthermore, it uses constant space, as no additional data structures or recursion stacks are required. The key reason this method works is that it directly focuses on valid paths, eliminating the need to explore unnecessary states. By leveraging the reversibility of transformations and the power of modulus operations, we ensure that the algorithm remains efficient and scalable. This is why we chose the reverse simulation method as our strategy. It is both time efficient and space efficient, making it ideal for large inputs where tx and ti can reach up to 10 to the power of 9. In contrast, the brute force approach, while conceptually straightforward, cannot handle such constraints due to its exponential complexity. Overall, the reverse simulation method provides an optimal balance of simplicity and efficiency, addressing the problem's requirements effectively. The problem we are tackling is to determine whether we can transform a starting point, represented as sx, sy, into a target point, tx, ti, using two specific operations. The first operation allows us to replace x, y with x plus y, y, while the second operation lets us replace x, y with x, x plus y. The goal is to check if, through a series of these operations, we can reach the target point from the starting point. A brute force approach to solve this problem involves simulating all possible moves starting from sx, sy recursively. By exploring every potential path, we can determine if the target is reachable, but this approach is computationally expensive due to the large number of paths that need to be evaluated. This sets the stage for exploring more efficient strategies to solve the problem. To implement the brute force approach, we follow a few key steps. First, there are two base cases. If sx, sy equals tx ti, we return true since we've reached the target. Conversely, if sx exceeds tx or sy exceeds ti, we return false, as it's impossible to reduce the values of sx or sy. The recursive step involves making two recursive calls, one simulating the move sx plus sy, and the other simulating sx plus sy. If either of these paths leads to the target, we return true. Otherwise, we return false. However, this approach has significant computational drawbacks. The time complexity is exponential, 2 to the power of k, due to the branching nature of recursion at each step. Space complexity is k, where k is the depth of the recursion. To address these inefficiencies, we can use an optimized approach that works by reversing the operations instead of simulating them forward. The optimized approach involves reversing the operations, starting from the target point, tx, ti, and working backward to the starting point, sx, sy. The first base case is that if tx ti equals sx, sy, we return true, as we've successfully reversed our way to the starting point. The second base case is if tx becomes less than sx or ti becomes less than sy, in which case we return false, as it's no longer possible to reach sx, sy. The key operation here is to reverse the transformations. If tx is greater than ti, we subtract ti from tx, effectively undoing the x plus y operation. Similarly, if ti is greater than tx, we subtract tx from ti, reversing the x plus y operation. This process is repeated until either tx, ti matches sx, sy, or becomes invalid. To further optimize this process, we can use the modulo operation instead of repeated subtraction. For instance, if tx is much larger than ti, performing tx% equals ti reduces tx in one step, significantly improving efficiency. With the modulo optimization applied, we can refine the steps further. While both tx is greater than sx and ti is greater than sy, we check whether tx is greater than ti. If it is, we set tx equals tx% ti. Otherwise, we set ti equals ti% tx. Once this loop exits, we examine the remaining values to determine if a direct match is possible. Specifically, we check two conditions, whether tx equals sx and whether the difference, tag sy, is a multiple of sx, or whether tie equals sy and the difference, tx sx, is a multiple of sy. If either of these conditions is satisfied, we return true, otherwise, we return false. The key insights here are that reverse engineering avoids redundant computations by only exploring valid paths, while the modulo operation drastically reduces the number of iterations, especially when one of the coordinates is significantly larger than the other. This approach also carefully handles edge cases, such as when tx is tie starts smaller than sx sy, or when one dimension matches but the other does not align. This approach is highly efficient and does not require any additional data structures. The operations are performed directly on integers, and in the case of the brute force method, the recursion stack is the only memory used, with a maximum depth of OK. When analyzing the complexity, the brute force approach has a time complexity of O2 to the power of k, due to its exponential branching, and a space complexity of OK, for the recursion depth. In contrast, the optimized approach is significantly faster with a time complexity of O log max tx at tie, as the modulo operations reduce the size of the numbers logarithmically. The space complexity of the optimized approach is O1, because it operates entirely in place without additional memory overhead. These improvements make the optimized solution well suited for handling large inputs efficiently. Let's walk through an example to better understand how the optimized approach works. Suppose the input is sx sy equals 1, 1, and tx tie equals 5, 3. Starting with tx tie equals 5, 3, we reverse the operations. Since tx tie, we calculate tx equals tx% tie, which gives 5% 3 equals 2. Now, tx tie becomes 2, 3. Next, since tie tx, we perform tie equals tie% tx, resulting in 3% 2 equals 1. The new values are tx tie equals 2, 1. Again, since tx tie, we calculate tx equals tx% tie, resulting in 2% 1 equals 0. At this point, tx is tie no longer matches sx is y, so the output is false. This example highlights how reversing operations and applying modulo optimizations allow us to efficiently determine whether the target can be reached. By focusing only on valid paths and reducing unnecessary computations, this approach offers a clear advantage over exhaustive simulation. This Python implementation solves the LeetCode problem number 780, reaching points by working backwards from the target point, tx, tie, to the starting point, sx, sy. The core idea is to reverse the operations allowed in the problem and reduce the target coordinates until they match the starting coordinates or become smaller than them. The function begins by entering a while loop that continues as long as tx is greater than or equal to sx and tie is greater than or equal to sy. Inside the loop, if tx is tie matches sx is y, the function immediately returns true because the target has been successfully reached. If tx is greater than tie, the function checks if tie is greater than sy. If so, it reduces tx using the modulus operation, tx% equals tie, effectively subtracting multiples of tie from tx to bring it closer to sx. If tie is not greater than sy, the function checks whether tx sx is divisible by tie. If this condition holds, it implies that tx can be reduced to match sx exactly by repeatedly subtracting tie. Similarly, if tie is greater than tx, the function reduces tie using the modulus operation, tie% equals tx, if tx is greater than sx. Otherwise, it verifies if tie sy is divisible by tx, which would allow tie to be reduced to sy. The loop terminates when neither coordinate can be reduced further, and the function returns false if the starting point, sx, sy, cannot be reached. This approach is efficient because it avoids simulating every step of the transformation process directly. Instead, it leverages the properties of the modulus operation to skip unnecessary steps, ensuring the solution runs efficiently even for large inputs. The time complexity is approximately O log max tx tie because the modulus operation reduces the larger coordinate significantly in each step. This is the complete Java implementation for LeetCode problem number 780, reaching points. The logic mirrors the Python solution, working backward from tx tie to sx sy. The key difference is the use of Java syntax with explicit type declarations and the class structure. The code utilizes modular arithmetic to efficiently reduce the larger coordinate until it matches the target or becomes unreachable. To solve this problem, we work backward from the target point, tx, tie, to the starting point, sx, sy. In this example, we need to determine if we can reach 3, 2 from 1, 1. Initially, both tx and tie are greater than sx and sy, so we evaluate which of the two values, tx or tie, should be reduced. Since tx tie, we reduce tx by taking the modulus of tx with respect to tie. This gives us a new value for tx, which is 3% 2 equals 1. At this point, the new state becomes tx equals 1 and tie equals 2. Now, we check if it's possible to reach 1, 1 from this new state. Because tx is now less than or equal to sx, we verify if tie sy, %tx equals 0. In this case, 2 to 1, %1 evaluates to 0, which confirms that the transformation is valid. Therefore, the output is true. Here, we analyze whether it's possible to reach 2, 2 from 1, 1 by following the same backward approach. Starting with sx equals 1, sy equals 1, tx equals 2, and tie equals 2, we first observe that both tx and tie are greater than sx and sy. This means we need to decide which value to reduce. Since tx is not greater than tie, as 2, 2 is false, we reduce tie by taking tie %tx. This results in tie equals 2% 2 equals 0. At this point, the new state is tx equals 2 and tie equals 0. However, since tie is now less than sy, 0 less than 1, it becomes impossible to reach the starting point. As a result, the output is false. In this example, we aim to determine if we can reach 9, 5 from 1, 1. Starting with sx equals 1, sy equals 1, tx equals 9, and tie equals 5, we observe that both tx and tie are greater than sx and sy, so we proceed to reduce one of them. Since tx tie, we reduce tx by taking tx %tie. This gives tx equals 9% 5 equals 4, resulting in the new state tx equals 4 and tie equals 5. Next, since tx tie, we reduce tie by taking tie %tx. This gives tie equals 5% 4 equals 1, leading to the state tx equals 4 and tie equals 1. At this point, because tie is less than or equal to sy, we check if tx sx, %tie equals 0. Here, 4 to 1, %1 equals 0, confirming that the transformation is valid. Therefore, the output is true. To analyze the time complexity of our solution, we focus on how the algorithm iteratively reduces either tx or tie using modulo operations. By starting from the target point, tx is tie, and working backward toward the starting point, sx, sy, we observe that each modulo operation significantly decreases the larger value. Specifically, the larger value is reduced by multiples of the smaller value, leading to an approximately logarithmic decrease. This behavior indicates that the number of operations depends on how many times the larger value can be reduced in this way, which is proportional to the logarithm of the larger value. In the worst-case scenario, the algorithm continues reducing tx or tie until one of them is smaller than the corresponding starting value. If we let n represent the maximum of tx and tie, the total number of modulo operations required is proportional to O log n. In the best case, the target, tx if tie, matches the starting point, sx, sy, immediately, resulting in constant time O1. On average, only a few modulo operations are needed, leading to a time complexity of O log n. Even in the worst case, the time complexity remains bounded by O log n, making the approach highly efficient. Now, turning to the overall time complexity, we can summarize it as O log max tx tie, where the logarithm is based on the largest of the two target values. Moving on to space complexity, the solution is designed to operate in constant space. This is because it only uses a few integer variables sx, sy, tx, and tie to track the current state during the execution. Unlike approaches that require data structures like arrays, stacks, or queues, this algorithm avoids any additional memory overhead. Furthermore, the implementation is iterative rather than recursive, so there is no need to account for a potentially large call stack, which could occur in a recursive solution. As a result, the space complexity of this approach is O1, making it extremely space efficient. When comparing this optimized approach to a naive solution, the efficiency gains become clear. A naive approach would simulate the forward process from Sx sy to Tx ty by repeatedly applying the allowed transformations, such as x, y, dash, x plus y, y, or x, y, dash, x, x plus y. While this might work, it suffers from exponential time complexity, as each step introduces two branches, leading to a worst-case time complexity of O2 to the power of k, where k is the number of steps required. Additionally, the naive approach would have a space complexity of O(k) due to the recursion stack or the need to store iterative states. In contrast, the optimized solution eliminates this exponential blowup by reversing the process and leveraging modulo arithmetic to skip redundant intermediate steps. This reduces the time complexity to O log n and the space complexity to O(1). The mathematical reasoning behind this efficiency lies in the behavior of the modulo operation, which reduces the larger value by repeatedly subtracting multiples of the smaller value. This ensures that the larger value decreases significantly in each step, with the number of operations being bounded by the logarithm of the larger value. Thus, the time complexity is conclusively O log max Tx ty. One of the common mistakes when solving the reaching points problem is assuming that the process of reducing Tx ty to Sx sy is always reversible. This is not true because the transformations are not symmetric. While forward moves like x plus y, y, or x plus y are valid, the reverse reductions, such as Tx ty ty or Tx ty Tx, may violate constraints or become infeasible. Another frequent error is overlooking the base case conditions. If at any point Tx becomes smaller than Sx or ty becomes smaller than Sy, further operations are impossible, and the algorithm should stop. Failing to handle this can cause infinite loops or incorrect results. Finally, using inefficient brute force recursion is a common pitfall. Trying to explore all possible paths without pruning leads to exponential complexity, making the solution impractical for large inputs, especially when Tx and ty can go up to 10 to the power of 9. Another mistake to watch out for is the incorrect use of modulo logic in optimized solutions. When reducing Tx ty by Sx sy, misapplying modulo operations, such as incorrectly computing Tx%ty or ty%Tx, can result in skipping valid paths or performing unnecessary iterations. Additionally, it is critical to validate constraints before performing reductions. If the algorithm does not check whether Sx equals Tx and Sy equals ty, it may attempt illegal operations, which could lead to undefined behavior. Ensuring these validations are in place is key to maintaining the correctness of your solution. To excel in interviews, it's important to focus on a few key insights. First, recognize that this problem fundamentally relies on understanding how modulo operations can help backtrack efficiently. Instead of brute forcing every possible path, think of the reduction process as being similar to finding the greatest common divisor. This allows you to prune unnecessary computations. Be prepared to handle tricky edge cases, such as when Sx Sy starts at 1, 1, when Tx ty is significantly larger than Sx Sy, or when one coordinate equals the other. For instance, consider Sx Sy being 2, 2, and Tx ty being 10, 2. Emphasizing an optimized modulo-based approach is critical in interviews because it demonstrates your ability to reduce time complexity to O log max Tx ty. Finally, communicate your thought process clearly, explaining how each step narrows the search space and avoids redundant calculations. If you're looking to deepen your understanding, there are several related problems that share similar concepts. For instance, LeetCode 365, the water and jug problem, also involves reachability logic based on the greatest common divisor. LeetCode 1443, which focuses on the minimum time to collect all apples in a tree, emphasizes graph traversal and pruning unnecessary paths, which parallels the optimization techniques used here. LeetCode 343, integer break, involves breaking down a target value into smaller components, which is analogous to reducing Tx ty step by step. Lastly, LeetCode 1254, number of closed islands, explores recursive problem solving in constrained environments, similar to how this problem requires careful validation and pruning. There are three main approaches to solving this problem, each with its own trade-offs. The brute force simulation approach involves recursively trying all forward moves, such as x plus y, y, and x plus y. While straightforward to implement, this method has exponential time complexity and becomes impractical for large inputs. The optimal approach is modulo-based backtracking, where you start at tx, ty, and reduce backward using modulo operations until you reach sx, sy, or determine that the transformation is impossible. This approach is highly efficient, operating in O, log, max, tx, ty, but requires careful handling of edge cases in modulo logic to avoid errors. Lastly, there's the mathematical insight approach, which leverages the properties of the greatest common divisor to determine whether tx, ty, can be expressed as a linear combination of sx, sy. While theoretically elegant, this method can be more challenging to explain or implement under the time constraints of an interview. Great job! Today, we tackled the reaching points problem using an optimized algorithm that simplifies the solution by working backwards. We highlighted key concepts like backward reasoning and modular arithmetic to achieve efficiency. Thanks for joining, and don't forget to subscribe for more engaging content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!